Okay, thank you. Good afternoon to everybody. Today I will go a bit slower than last time because last time I wanted to provide a general introduction on transport, energy, and emissions. So I don't know how many of you were present already last time, but I introduced the impact of transport system on the energy consumption, then the relation of transport system with emissions, both at local level, so pollutants, and global level, CO2. And now we concentrate on energy carriers for low emission private mobility. So how far we can push electrification, what are the alternatives, what are the architectures of different powertrains, so to understand where our future motorized mobility can be, and which kind of powertrains, which kind of fuels. So this is the core. In particular, I would like you to have these points, these 5 points in mind, which are the energy carriers for motor vehicles. So at the end of this lesson, I would like you to, let's say, be strong, or at least to know which are the energy carriers for motor vehicles, provided that we are trying to find alternatives to oil-derived fuels. Then the second one, how we can push low emissions. Consider that emissions concern both local and global emissions, as we already know from the last lesson. Then the third point, I would like you to have a vision, at least a synthetical vision on legislation. The fourth point is, what can do batteries? What are their energy densities, especially if compared with alternatives? And the last point is, which alternatives are there, or can we envisage as possibilities to conventional powertrains and fuels? So what are the alternatives to what we are accustomed to? So these are the 5 points. I resume 2-3 slides from last time because I'm not sure that you were present all in my last lesson, but these are the points. First point is European Union has stated already some years ago, but in the years has modified the vision. The first time was in 2014, a reduction in CO2, an increase in renewables, an increase in energy efficiency. And this doesn't concern only transport domain and mobility, but every field. Within transport domain and mobility, we will concentrate on them because they concern transport and mobility, considering one thing, that we can push in particular the reduction in CO2 through modal shift, railways, metros, people movers, ropeways, through technologies, powertrains, intelligent transport systems, and through applied maths, that means optimization. I already told you this last time, but I'm resuming because I will use this concept today. And the first two in particular concern transport planning. I also remember that greenhouse gas emissions are not only provoked, or the contribution is not given only to CO2, but also to natural gas or methane gas and to nitrous oxide. If you release natural gas in the atmosphere, it contributes to greenhouse gas emissions much more than CO2. And then I will also remember this last, then I will start with the new concepts. That is, last year, 2024, the Directive 2881 was published by European Parliament and the Council, and it concerns the level of concentration of pollutants in mainly our cities, where great part of the mobility and population take place or live in Europe. So, resuming, we have this goal of reducing CO2, increasing efficiency, increasing renewables. We have also the goal to contain emission of CO2, which is a global problem. At European level, we have this goal of containing local emissions, and in particular looking at the concentration of them, especially in the cities. And this table is accompanying the Directive 2881 of last year, which will be in full operation from 2030, and which regards the concentration of pollutants, mainly, as I said before, in our cities. Okay, so this is the list of alternatives that nowadays we have in front of us once we decide or we accept that crude oil on the top left side of this slide is no more the unique source we rely on in transport and motorized mobility. Because so far, in road transport, in air transport, in maritime transport, partially in rail transport, when we don't have electrified lines, we rely on crude oil in the transport domain. All the other fields have other sources. In the transport domain, we rely in a nearly monopoly condition on crude oil. If we consider that this can be, let's say, a source that cannot be, let's say, lasting for decades, or if it will be more expensive, or if we have to attack the North Pole or Greenland to obtain crude oil beside deep oceans, or if we consider that pollution coming from crude oil are all relevant elements, one or more of them, then we have to look at alternatives. Natural gas is the, let's say, simplest one in many countries because we have already pipelines for natural gas. Coal has been abandoned since since 2 centuries in the transport domain with the steam locomotive, I would say, and nuclear sources, but mainly related to some applications and typically for military purposes, not civil ones. But we have to consider renewables, wind, hydroelectric, sun, geothermal, biomasses as possible sources, in particular for power production plants. And this power can be used for either producing fuels, biofuels, e-fuels, or for recharging batteries, or even for preparing fuel cells. So the message of this slide is this. We still have one main source, crude oil, with oil-derived fuels. Once we look at alternatives, these are the alternatives, and their applications are on the right side of this slide. What we want to do is to understand how far each of them is a viable solution, the pros and cons of each of them, and if electrification can be the solution or one of the solutions. So the first point is that once we decide to abandon the monopoly of crude oil, what we have to see is if the source, the energy source that we have in mind, is available in nature as its own, or if we have to prepare the fuel. In this kind of analysis, if we think, for example, at a battery, we need to analyze the well to wheel. This concept already was introduced last time. That means from the well to the tank and the tank to the wheel. But we don't have only to analyze the energy chain of the fuel or the energy carrier, but the life cycle of the vehicle. Because if we have to, let's say, emit a lot of CO2 for building a vehicle, a motor vehicle, then it means that the CO2 will be emitted there in the life cycle, though not necessarily during the operation. For example, an electric vehicle could seem to avoid the emissions of CO2 at the tailpipe because the electric vehicle has not the tailpipe, but in the life cycle approach, we have to consider that for creating that vehicle and that battery, the CO2 has been emitted before. Okay, given this general premise, I recall the fact that as regards CO2, in 2011, European Union introduced for the first time the concept of containing the emissions of CO2 by the car makers within their fleet, passing from a threshold of 130 grams of CO2 per kilometer to 95 grams of CO2 per kilometer in 2020, actually 2021. Then in 2023, February, European Parliament said, well, let's bring this 95 grams of CO2 per kilometer to zero. And this has opened a wide discussion. We will see this later. As regards light duty freight vehicle, this threshold has passed in 2015, 175 grams of CO2 per kilometer to 147 grams of CO2 per kilometer in 2021, actually, end of 2020. Okay, which are the regulations which started this evolution? These two, 510, so looking at my goals of today, this is the legislative vision, the regulation 510, 2011, and the regulation 397 of 2013. And this concerns the, sorry, some parts from time to time are in Italian, but you have the text in English too. This regards both the motor vehicles and the light commercial vehicles. It was the first time. Before that date, there were just the Euro 1, 2, 3, 4, 5, 6 as classes of emissions, but looking just at the local emissions. Okay? Local emission, pollutants, and global emissions, CO2 in particular. In 2011 and 13, European Union started analyzing these values, okay, with an environmental relevance that was, let's say, was becoming important in these years. Okay, skip this slide. As regards the internal combustion engines, sorry, this slide is in Italian because I had prepared it that way, but I comment it rapidly. In 1992, when there was a first feeling about the environmental impact, and so the environmental concept of within the sustainability of transport systems, so a sustainable mobility in terms of emissions, well, in 1992, the first class of engine was introduced, and it was the Euro 1. Okay, then in 1997, it became Euro 2, then in 2001, Euro 3, in 2006, Euro 4, in 2008, Euro 5. Then Euro 5 had two steps, Euro 5A and Euro 5B. The Euro 5B introduced some filters for the particulate matter, so reducing much the particulate matter produced by internal combustion engines. And then the Euro 6, that is the actual one, was introduced in September 2014 with different versions. Euro 6B, 6C, D temp, and D. Then from the 1st of July this year, the Euro 7 will enter into force, Euro 7. It was prepared, it was, let's say, emitted for the first time in November 2023, but the application of it starts this year. Okay, so at a certain moment of the history of this classification, as I was saying before, in 2011, also CO2 was introduced as an important element to be considered, but not at each vehicle, but in the fleet of each car maker. We will see it later. Okay, then in 2019, the regulation 631 introduced a certain number of specifications confirming the value of 95 grams of CO2 per kilometer that was stated some years before, but also introducing some reduction in the emissions that the European Union wanted and still wants from the car makers in order to obtain in the next years, a containment of, in particular, the CO2 generated by the fleet of each car maker. I don't enter into the details. For me, it's important that you understand this evolution, and then we will see how we can pursue it. What about the effects of this? Well, if the car maker is able to reduce the average value of its fleet underneath the threshold, in this case 95 grams of CO2 per kilometer, then it will receive super credits. But nearly none, no car makers are able to do this. Then if they have values that are higher, they have to pay a penalty. And this year, the car makers have asked to suspend the penalty because they are not able to satisfy all the very, let's say, important, relevant, but also difficult to apply goals that European Parliament has stated. So we are in this moment a great ideal of containing both local pollutants and global emissions of CO2, and a very difficulty of the car makers to apply them farther than 95 grams of CO2 per kilometer. And we are at this point. This year, the European Parliament allowed it to spread these satisfaction of the limit of 95 grams of CO2 per kilometer with the consequent penalties on 3 years. But it's not a solution, it's just a way of, well, let's think about it. Okay, then, as I said before, this Euro 7 classification of engine started 3 years ago, but with application from this year, and it was approved by the Parliament in April 2024. Consider that there are some difficulties to win because a car maker cannot at the same time go towards zero emissions and Euro 7, because there is a time for using the plant installations. I mean, a certain number of years. Not that it's not true that we can invest in a certain line and then after a few years change it, because you would have, let's say, some difficulties also from the economical point of view. Okay, what is the innovation of Euro 7? Well, it doesn't consider just the emissions from the internal combustion engine, but also from tires, tire abrasion, and from brakes. These are the three main sources: brakes, tires, and engines. So, of course, these concern any kind of vehicle, also the electric one, in particular the tire abrasion. Then, as regards buses and heavy trucks, I don't enter into detail about them because it is not part of this lesson today. But anyway, they have been introduced recently with some different, let's say, viewpoint concerning them. In any way, what is now considered with Euro 7 is the introduction of the concept of life cycle. And this is important because, as we understood also from last time, it's not only important a local level emission from tailpipe, but as I said before, the well-to-wheel and the life cycle of the vehicle itself. We need to recall that the white paper published already in 2011, stated that the challenge in Europe is to break the transport system dependence on oil, but without sacrifice its efficiency and without compromising mobility. So we have to think, when thinking about alternatives to oil-derived fuels, to engines, motors that are, let's say, not sacrifice efficiency, neither compromising mobility. Is the European Union the only one that 2 years ago has stated this zero emission goal? Yes, because other parts of the world, as you can see in this slide, United States, China, Korea, and so on, declared some reductions, important reduction, but none of them said ban, IESC ban, internal combustion engine ban. And this is under discussion now. It's an important matter because we know that European Union relies a lot of its competitiveness on the production of motor vehicle, notwithstanding the fact that we are pursuing a hierarchical, differentiated, flexible, multimodal approach to mobility, because we can use the train from city to city, we can use the car, we can use the bike, we can use different modes. Notwithstanding that, we have an industry, so we have to keep care about the effects of, let's say, making this industry close in case cannot pursue the goal that have been stated. How can we contain CO2? Okay, we can reduce the kilometers, of course, with an internal combustion engine. We can use for less time the internal combustion engine, and for example, an hybrid powertrain can do that because we can split the electric part of the traction from that obtained with an internal combustion engine, and we can operate on the efficiency. To operate on the efficiency means that we can operate on aerodynamics, on speed and acceleration, deceleration phases, on the specific rolling resistance of the vehicle, and on the mass and the dimension of the vehicles. Beside that, we can also operate on the driving behavior, considering that typically these CO2 emissions come from an element that I introduced last time, that is the conventional driving cycle. I don't know how many of you are confidential with that. There is a conventional driving cycle that is called WLTP, World Harmonized Light Vehicle Test Procedure, which when applied implies a certain number of emissions at local level and at global level. It was the one which was which arrived to the newspaper with the Dieselgate. So the fact of influencing through the software the emissions in order to contain them and not pay taxes according to their emission, to these emissions. So having I hope, the picture clear, so where does the CO2 come from and how we can influence that, let's see how we can modify the powertrains and which are the alternatives. The picture that I introduced a bit last time, now I will recall it and enter into more detail. The first level is a micro-mild hybrid. That means we just have a belt-driven starter generator. We don't have an independent electric traction, but we can reduce the emissions because the internal combustion engine is assisted to some extent, and you have a battery which can do some activity. And also you can recover part of the energy during the braking phase. Then you have a real hybrid solution, which can be either parallel or serial hybrid. We deal with transport systems, so we don't have to be expert in engines, but at least I let you understand which are the main elements. In the parallel hybrid that we will see shortly, we have the alternative of internal combustion engine and electric traction, but they can collaborate. The electric motor can collaborate with the internal combustion engine and assist it during the acceleration phases, so reducing its power. And also it can collaborate with the internal combustion engine and with the braking phases, because instead of, let's say, transforming into heat the brakes, the power when you need to brake, then you can reverse the electric motor in order to recover energy that can be provided to the battery. So you see a collaboration, and you can also use one of them, of the two engine or motor. In serial hybrid, instead, you have the electric motor and internal combustion engine in series. This comes mainly from electrical engineers who say, well, let's put the internal combustion engine with its tank, but instead of connecting it directly to the wheels, we use it to provide energy to the battery and to the electric motor so that the internal combustion engine works at its optimal conditions. And so we can contain emissions and make it more efficient. Then on the right side, we have the extreme solution, that is all electric. I avoid to use the internal combustion engine. I put a battery, I put an electric motor, and the vehicle goes like that. Or a fuel cell. The energy is stored in fuel cell, typically of hydrogen, and then you have an electric motor which uses the energy stored there to move the vehicle. Okay, I hope it's clear. Let's see into a bit more detail how do these work. This is the architecture of a serious hybrid electric vehicle. So as I said before, this was born in electrical engineering. You have an internal combustion engine which works at the top, typically around the top of its conditions. So in the map, it's working well. And through a rectifier provides electricity through the rectifier. Before it's just a movement, then it becomes electricity for the battery, and through the inverter to the electric motor, which is that which moves the wheels. Okay, this is in series. The main alternative to this is, well, this is again a series, but you have the motors, the electric motors on the axles. So the concept is similar, but it's the same architecture. Then the alternative is parallel hybrid electric vehicle. In parallel, you have the engine, as I said before, internal combustion engine, and the electric motor. So the electric motor assists the internal combustion engine, and during the braking phases, it recovers energy to put it into the battery. And again, this is positive because you have a downsizing of the power of the internal combustion engine, and you recover part of the energy. And this allows to reduce both emissions at local level and global level. Then you can have a mixture, a series parallel, that is an architecture like that, again with the inverter, generator, engine, electric motor, battery, and then mechanical coupling to provide power to the wheels. Then you have the possibility to have a four-wheel drive system in a more complex architecture. I don't enter into much detail, but the concepts are similar. So you can have both the power in the front and rear axles of the vehicle. And last but not least, the most flexible architecture, that is the plug-in hybrid. The plug-in hybrid allows you to both recharge the battery by using the internal combustion engine or by connecting through a charger to the electric grid. So this way you can use the internal combustion engine or the electric motor or both of them, and you can recharge the battery using the internal combustion engine or by connecting the vehicle to the grid. And this is the most flexible. But given the fact that it's the most flexible, it's also the most expensive. And so it's like having two vehicles in one, but it allows you to move, for example, with electric traction in a city and with internal combustion engine outside the city. And since you can use outside the city the most, let's say, efficient parts of the map of the engine, then it means that you gain in terms of emissions, both at local level and global level. Having no emissions at the level of the city and having low emissions outside the city. What about the batteries? Remember that one of my goals today is to let you understand what are the energy density of the batteries and to compare these densities with those of an oil-derived fuel. Well, this is a picture of the condition, more or less, of the batteries. It's a bit old with some evolution, but it's still actual. Well, we are around this area. That means lithium-ion, lithium polymer, lithium metal batteries towards zinc air. But what I underline is that the density, the energy density is around 200, 300. And with solid state batteries, we are going towards 400 kilowatt hour kilogram, not much more by 2030. I don't know how sensible you are in terms of energy densities, but if you compare these values with the energy density of oil-derived fuels like gasoline, like diesel, well, crude oil has an energy density of 42 megajoule per kilogram, which transformed into kilowatt hour per kilogram makes 11.67 watt kilowatt hours. That means 11,670 watt hour. You have to compare these 11,670 watt hours with 200. So this means that the energy density of the best of the batteries is at least 60 times, even 90 times less than the energy density of an oil-derived fuels. This means that to have the same autonomy than that you have with a tank, an internal combustion engine, you need a battery that is much, much bigger. But you recover part of this ratio with the fact that the electric motor is much more efficient than internal combustion engine. Typically, an internal combustion engine at the top of its efficiency nowadays arrives to 48%, 48 by itself. Then if you apply it on a car, you lose part of that because you have the transmission and you arrive at 38, 39, something like that percent. That means you insert 100 and you have at the wheels 38. But in the cities, you have the lowest efficiencies because you have the start and stop, you have the queues, you search for the parking, you have the traffic lights, and this means that the efficiency of a conventional engine goes down to 16, 18. This is very low. On the opposite side, you have the electric motor, which again has a variation in its efficiency, like 86, 88, 90, 92%. So interesting. From a superficial way, it's winning, no problem. It doesn't create emissions, and it needs some electricity, of course, and it has a long-lasting life because it works for many, many, many years. So this means that we have this comparison. Being the efficiency of an electric motor higher than that of an internal combustion engine, the ratio of the energy densities of which I spoke before is not so high because you recover part of it with the efficiency. I think it's clear from an engineering point of view. And what about the consumption of a BEV? BEV stands for battery electric vehicle. Well, nowadays we are around 0.11 up to 0.25, 0.28, but in normal conditions. Because if you work at low temperatures, less than 5 degrees, 0 degrees, or high temperature, more than 20, 25 degrees, centigrade degrees, then you have an increase of consumption even of the 50%. Why? Because the battery, to work well, has to condition itself. I don't know if you found your mobile phone, your smartphone switched off in summertime because of the heat. In Italy, it happens from time to time. The temperature raises and it has to switch off, saying, well, it was too hot. This cannot happen on a car. So this means that the battery has to use part of its energy to refresh itself. And the same happens underneath 0, 5, 0 degrees because the battery cannot work if it's too cold. So it has to use part of its energy to heat itself. And then while inside the car, you use the heat from the engine to provide air conditioning of the passengers, of the vehicle, then of the passengers. This cannot happen with the electric motor because you have to produce that heat somehow. So this means that those consumption kilowatt hour per vehicle per kilometer are in normal conditions, but the it's called also energy management of the battery. The self-conditioning of the battery and the conditioning of the inside part of the vehicle imply 50-60% even of increase of consumption. Okay. Given that, we have some possibilities for the batteries like ultracapacitors, lithium-ion batteries, as you can see here, which imply lighter and smaller batteries. But for the time being, a revolution is not foreseen. And consider that it's around 30, 40 years that chemistry is working on batteries. So far, a revolution is not envisaged. We have to deal with an electrochemical process to be compared with reversing a liquid fuel as we are accustomed to. Okay, and so this is more or less the picture concerning batteries. But to complete the scene, to understand which can be the most promising alternative or which can be the most promising alternatives, we need to know which is the use. So the point of view of the demand that so far seems to be a bit neglected. So I start quoting a couple of sources in literature. This regards a comparison of daily distance covered by automobiles. Looking at all literature in the world, we found that from 25 to 37 in the United States, even 46 or 52 kilometers per day is the typical average value for each automobile. In Europe, we drive a bit less. In United States, they drive a bit more, but more or less these values are all the same order of magnitude. Okay, given that it's not enough, because we need to know the distribution. It's not enough to have an average value. We need to know the distribution. So where are these vehicles used? In motorways, in urban context, and how frequently they are used there, or in extra urban context. Here I quote another source where you can find, according to a big data concerning actual use of automobiles, how these vehicles have been used, are typically used. And what we can typically find in literature and outside the world is an hyperbole where you have frequent short travels, typically in urban contexts where 3 people out of 4, as we have seen last time, live in cities. So they express their daily mobility for short distances and very frequent, 4, 5, 6 days per week. And longer travels are typically associated to the weekend or to occasional travels for work, or more or less occasional. Anyway, this hyperbole says, well, we have a frequent and short range, typically daily mobility, and we have a less frequent with longer range mobility, motorized mobility. And what about idle times? That means how long these vehicles are kept in a parking area. This is the slide which shows that. So typically we have for short times when we are at the traffic lights, with the red light, of course, and when we stop for a while for shopping for a while, or there are longer times where we are, for example, sleeping in the night and the vehicle is there parked. But this is useful too, because we have to understand if moving towards electrification, we have the time to recover the power that we've used in a typical usage that we have seen before. So given that, we have to compare that power with that of the grid at local level and at regional level. I took this as an example for Italy. 90% of Italian people have a contract up to 3 kilowatt. So this means that on the right side, according to the kind of battery, PHEV stands for plug-in hybrid electric vehicle, 25 stands for the number of kilometers of autonomy, 25. You can see that it's green where it's compliant with the number of hours that you have in the first column and the power that typically citizens have in their houses. And once you increase the dimension of the battery, the probability to be able in a few hours to recharge this battery on a normal base, so with a normal contract, is more difficult. So to do that, you have to address fast and rapid charging, which imply a higher voltage and even a higher cost. Just a glimpse on the maps of the engine so that we can arrive later to the conclusions. Well, on the top right side, you can see the map of an electric motor, 84, 86, 94%. It depends on how it works. So it's fine. The weak element of the full electric vehicle is not the electric motor, it's excellent, it's the battery, because of its density, of its increase of mass, and of its electrochemical process to recharge it. So you need time, you need power. On the right side, you find instead the map of an internal combustion engine that arrives, as I said before, to 48% nowadays, the top a bit less in older engines. And what we can do is, I said before, to let them collaborate together. You can see that the engine evolution in terms of efficiency, the goal of European Union, and particulate in terms of local emissions, is interesting because passing from Euro 1 to Euro 7, we have continuously decreased the particulate mass limits and consequently the local emissions, but also the global ones in terms of CO2 that I mentioned before. How can we recharge them this way? So, provided that we understand that each of the solutions has its pros and cons, if we address the possibility to recharge the vehicle on the grid, we can either recharge with a wire or wireless, or with a contact. Here it is, or with the battery swap. The battery swap means to replace entirely the battery. Consider that those density, if you want to guarantee a certain autonomy, means a certain amount of mass. So it's not typically compliant with the strength of a person. It can be if you're dealing with a motorbike, a rickshaw, or something like that. Otherwise, you need an instrument. Some companies have already promoted in the last decade a solution based on substitution, so battery swap. But you need to be there and you need to standardize the battery. But especially you need to be there where you have to change it. And this is the most complex thing, typically when you're moving anywhere. Maybe in the cities or maybe at home. You have two batteries, you arrive at home, you change it. But it's your own battery and you do it at home. So given that, we have to face as transport systems engineers, professors, researchers, whatever we are, we have to check these number of possibilities in order to address a solution that is compliant with what we said before, that is efficiency and not compromising mobility. Some solutions also proposed some mobile vehicles that can arrive where the vehicle needs, but again, you need to reach them. Maybe if you are in a flow, in a traffic flow, and you cannot reach the vehicle, how can you solve the situation? I don't know. Then another issue is, if we move towards full electrification, is to analyze the queues. Because if you have a one-to-one possibility, then it's fine. If you don't have a one-to-one possibility, and typically it regards people who don't have the possibility to recharge neither at home, not at a working place, then applying the queue theory, I don't know if you are expert in the queue theory, but provided the number of services and the distribution and the number and the distribution of the demand, you can quantify the length of the queue in terms of meters, kilometers, and the time in the queue. So given that, if we imagine the scalability of electric vehicles, we have also to calculate the effects on the queues. So maybe, again, a compromise or an integration of solutions could be the best thing. Of course, we can reduce the queue if we, and the waiting time, if we enhance, if we increase the power. But this means, again, an increase of cost, because while a normal recharging costs like 20, 30, it depends where we are in Europe, cents of euro per kilowatt hour, if we address fast and rapid charging, we arrive to 40, 50, even 90 and more cents of euros per kilowatt hour. So it means that we pay more for recharging than for refueling. So how can we charge this battery, as I was saying, with a wire, but also wireless, with inductive charging, in a static way or while driving? So those who push towards a full electric market say, well, we can keep the lanes of streets, of motorways, with the possibility of making inductive charging. That means charge while driving. This is a cost of infrastructure not so marginal, and according to some proponents, this could be the solution. But considering also that you should do it in many places on the infrastructure. This is an example, sorry, it's in Italian, of a bus already existing since 2003 in Turin, the city where I live, working with inductive charging. When the vehicle arrives at the terminal, you have the change of the driver, and during those 5-10 minutes, the battery is recharged with inductive charging so that you can have the autonomy for the next service. And this possibility is a static wireless charging. But of course, it's more, let's say, fruitful, or it's more suitable for a fixed path circuit, so typically for public transport. So when you know where the vehicle has to go and when the vehicle has to stop, more or less. In this kind of charging, I mean, that we have just seen, the inductive charging, consider that the air gap has an influence on an efficiency. So we were speaking about efficiency, but if you have a big air gap, you even lose 50% of the power you provide. So if we think again at the well-to-wheel, We have to provide the electricity. It depends where it comes from, because if it comes from coal, it's not winning at all. If it comes from natural gas, we have a certain efficiency in the production of electricity, in the distribution of electricity. You lose something like 6-7% in distributing electricity. In recharging, you lose some points percent. In aging effect of the battery, you lose 10-15% after 2, 3, 4 years. And then in the kind of recharging, if you have, for example, an air gap like this, you could have a loss of power in inductive wireless charging. And then you have the efficiency of the engine itself. So apparently, it's very good to have an electric motor, but we have to consider the energy chain. Apparently, it could be better to have, let's say, an electric motor, but we need to consider the recharging of the battery and the well-to-wheel without losing the life cycle analysis. Okay, so I arrived at the conclusions with 2 slides, and I leave, sorry, look at the time, yes. Well, I have some minutes for the last 2 slides, which require some minutes, 3, 4 slides and a few, and then I would leave some time for the questions. So what are the alternatives so far, considering what I said before and what I said last time? For light-duty vehicles, I've represented this flower where you see on the top the hybrid diesel-electric. This means that when you accelerate, as I said before, according to the powertrain that you use, you can assist the internal combustion engine with the electric power, and this means downsizing, and this means less emissions. You can also have a solution with sufficient enough autonomy with the electric battery, which allows you to move in a city without making local emissions. Then you can have going on the right side, the diesel also with biofuels and e-fuels. That means you maintain a conventional powertrain, a conventional internal combustion engine, but you insert a different fuel that is more bio. I don't know if you heard about HVO fuels like this, which are greener, and possibilities also to insert biofuels. That means that you grow plants, which during the growing phase, they absorb CO2, and then when you burn them, they emit CO2, but the well-to-wheel analysis brings to 0 or something like that. Okay, and even e-fuels, which are produced from, let's say, a synthesis process, an industrial process. Then you have liquefied petroleum gas, not so promising, but could be an alternative already used, of course. And then the natural gas on the bottom part of this picture. That means you can either compress it, and this is typically used in the cities or in cars, in the cities for buses, or liquefied. To liquefy a gas means to invest power, to lose in efficiency, but to provide more autonomy. So this is not typically done when you have to deal with long travels. So heavy-duty vehicles and buses which work outside the city context. And then you can have the electric. The electric can be both in the version of plug-in, so you have a full electric vehicle and you plug in. When you have to recharge it, you have to stay for a certain amount of time to recharge it, and you need a place where you can recharge it. Or an electric, but with the catenary. That means the trolley or in-road charging, as I said before. These are the alternatives. All of them with pros and cons, all. And maybe if we reduce the number of alternatives, we can reach economies of scale. On the right side, top right side of the slide, you can see instead the heavy-duty vehicles. Similar solutions, but avoiding some of them. So you can have liquefied natural gas instead of compressed, diesel, biodiesel, like HVO, compressed natural gas, less used, hydrogen. Hydrogen, as you know, is abundant in nature, but it's in the water, it's in the natural gas. You have to separate the molecules through hydrolysis, for example, and for the water, and this implies power. So the separation of the molecule of hydrogen implies investing in energy, and sometimes you have to invest more in energy than the energy that you can store. Then, last but not least, electric. But of course, for high masses, it's not convenient because the density of the battery implies an increase of mass, so it's better in that case to reduce the size of the battery and have a catenary or in-road charging. So these are the alternatives that nowadays we have in front. Given that, what can be winning? I already introduced this concept last time. If we have to deal with short travels, typically we will address mainly battery electric vehicle. Long travels, high masses, it's better to have internal combustion engines with the intermediate solutions of hybrid electric powertrains, even plug-in. Then, if we address short trips in city context, it's better to have recharging possibilities, otherwise we will have a lot of queues, and with hybrid solutions for solving the various proposals or let's say situations. A more battery intensive or internal combustion engine intensive market according to the elements that I said. Then as regards the internal combustion engine itself, according to what I said, you can use biofuel, e-fuel, natural gas, or let's say B-fuel or dual fuel engines. For example, you can use biogas and diesel. There exist engines which are suitable for both of them. Or you can use hydromethane, natural gas, and hydrogen. These are solutions that we can envisage nowadays for the next future. The higher is the mass, the higher is the distance, most probably the higher is the possibility, the probability that you will use internal combustion engine. So concluding, internal combustion engine has pros, the energy density, the time and easy fueling, so it requires less time, you just reverse the liquid, and the existence of an existing network. These are the main elements, not the only ones. The electric motor has a motor efficiency and a recharging time which doesn't allow to be so, let's say, winning with respect to the internal combustion engine. But if we look at the local pollution, this moves towards electric. So the best solution in my point of view, but this is an opinion, is, as I said before, to let these alternatives to collaborate, not to be one against the other, because each of them will lose. And if they collaborate, they will be winning, provided that we are not looking anymore to a full mobility made of motor cars, but hierarchical, flexible, multimodal, but the car has a role. And the industry in Europe has an important role. So we have to provide a solution that is compliant with the demand and with the constraints that we have seen so far. That's all. I've concluded and I'm available for any question, hoping to have satisfied your curiosities.